Okay, the broadcast is live. We still have 1 minute to go. So we already have some viewers on the broadcast. We'll start in a minute. Okay, so welcome everyone to the first Quantum Plus Hangout in this year. And it's a great pleasure to welcome Nicole Halpern from Caltech. Many of you will know Nicole also from her excellent blog posts on the quantum frontier. But today she's going to talk about her science. And the title is Towards Physical Realizations of Information Theory Models for Small-Scale Quantum Thermodynamics. Thank you very much, Nicole.
Yeah, thanks very much for having me. Thank you for the introduction and the invitation. To everyone else, good morning, good afternoon, and good night to various ones of you. Thanks all very much for coming out, especially at this unusual time, and especially to a talk that has probably too long a title. Let me see about sharing slides. Everyone seeing my slides now? Okay. The story of this talk starts with the story of a seminar that took place about 2 years ago. I was giving a talk about these two subjects, thermodynamic resource theories for models for heat exchanges and other statistical mechanical processes at small scales, for some meaning of small scales. One-shot information theory is a mathematical toolkit that is applied within thermodynamic resource theories. So the talk was a quantum information theory talk, fairly abstract and mathematical and technical. Probably wasn't the best topic for this crowd because I was talking to a bunch of condensed matter and optics theorists and experimentalists. At the end of the talk, my host, who is also a friend, stood up and said, "Oh, thank you for this talk. It was a bit abstract." And this person here, and he pointed to someone in the audience, said, "This is your worst enemy. He's an experimentalist. He's going to want to know, what does this model of yours have to do with what he'll see in the lab? You mentioned a bunch of phenomena. Will he observe them? You mentioned there was basically one slide with some experimental connections. That's what I want to hear more about." I said something about how this theory is very new, it can take a while to get to experiments, and also the theory is intended to illuminate fundamental limitations on what is ultimately physically possible. But he had a good point, and his question has been burning in my mind for the past 2 years. That's what led to this paper. I apologize if any of the images or fonts do not look quite right. I created this PowerPoint and then had to convert it to 2 different formats in order to get Google to play it on the Google Hangout. So I apologize if it still doesn't look perfectly right, even though I tried to do some polishing. This paper, not sure if Ian Durham is here. I think he signed up to be in the audience, but he's another reason for this paper. So you can thank him for giving me a little kick to write it, because this is going in a book of conference proceedings he's co-editing. I have to warn you, this talk probably won't be technical enough for the theorists, and it probably won't be physical enough for the experimentalists. So I'm not sure I'm going to please anybody, but there are a few points that I think would be useful that we can go through. First, I'm going to introduce the models that I mentioned and the mathematical toolkit that I mentioned. I'll argue that these models should be realized physically. I'll discuss what about them we might want to look for. I'll argue that now is the time to try to observe these effects experimentally. I'll offer some suggestions and some questions that can help us bridge the gap from the theory to the physical realization. What I really would like to do is initiate conversations between theorists and experimentalists and within the theory community itself. First, I'd like to talk about the resource theory framework. We all have some idea of what a resource is. A resource is something useful, and things are useful when there are constraints, when there's scarcity. Different things are useful in different contexts. The resource theories are models developed within quantum information theory. Resource theory is a model for scarcity and what transformations can be implemented by an agent who has only certain skills and certain tools. The most famous resource theory is the resource theory of pure bipartite entanglement, which is a rather long name, so I will call it entanglement theory for short. What do we do when we use a resource theory? We have in mind some agent, some experimenter perhaps, who has certain tools and certain skills. Using these tools and skills, the agent creates and manipulates quantum states. For example, in the entanglement theory, we suppose that the agent is a relatively classical person who has trouble creating controlled entanglement. Nowadays, some quantum optics labs, for example, have what people call push-a-button entanglement, so they have a little more control over entanglement, but roughly speaking, it can be difficult to create controlled entanglement. This is why quantum computing is such a big challenge. So we approximate this agent in the entanglement theory as given access to local operations and classical communications. Those are free. The agent can perform any unitary on the qubit that he or she possesses, can measure that qubit, and can also talk on the telephone with a friend. By the way, if you see my cursor and moving over the telephone, could you nod just to let me know? Nodding. Okay, great. That's in the entanglement theory. When we study a resource theory in general, we study transformations, for instance, from a quantum state rho to a quantum state sigma. We might calculate, can this rho transform via these easy operations to a state sigma, to which sigmas can rho not transform? If I have this many copies of rho, how many copies of sigma can I create? What is possible and what is impossible? There are three important properties that are very closely intertwined that characterize a resource theory. The free operations, such as local operations and classical communications and entanglement theory, model what the agent can do easily. Free operations include the creation of free states. In the entanglement theory, entanglement is difficult to create, but we suppose that the agent can create any non-entangled state for free without paying any cost. That's a simplifying approximation. Any state that is not free is valuable, is a resource state. For instance, in the entanglement theory, if there's a pair of qubits, then the most valuable state that those qubits can occupy is a Bell state. One reason to see why that's reasonable is if you have a Bell state and local operations and classical communications, then you can simulate a quantum channel. You can do something useful with that resource. There are many different resource theories. I'm going to focus on thermodynamic resource theories, which model interactions between a system and a bath. There have been many papers on the subject. These actually aren't necessarily, they aren't quite the original papers. Those I would characterize more as by Jansing and others, and by Lieb and Ingvesen. These are the papers I go back to the most. They're actually published a bit before, they were first released a bit before 2013, but since these were released, the literature has exploded. Over the past few years, so many papers have been written about this subject, I cannot keep up with the literature. So the topic is timely. There are a few reasons for thinking about thermodynamic resource theories. This is the cover of the paper, one of the papers that I presented on the last slide. Notice that the title contains the words fundamental limitations. These models, resource theories, are very simple models. We assume that the agent has an awful lot of control. That's sort of a disadvantage because it doesn't model reality completely, but it's an advantage because we can calculate easily. So we might want to ask questions like, even if an agent had a lot of control, what is the most that he or she could perform that is consistent with the laws of physics? What are the ultimate limitations? That sort of theoretical drive is one of the reasons for studying thermodynamic resource theories. Another motivation is technological. Very roughly, the argument goes like this. We are familiar with ordinary statistical mechanics that was built to describe about Avogadro's number of particles. It involves ideas like work, heat, and entropy. Those are originally associated with thermodynamics. But now in labs, people can control very small systems. People can stretch single molecules of DNA. They can send single electrons through a wire. There are people who are rebuilding or building from scratch with artificial systems, motors of the sort that you would find in biological cells, and certainly people mess a lot with entanglement. In many of these contexts, those thermodynamic concepts of work, heat, and entropy remain relevant, but these systems are so much smaller that we might expect conventional statistical mechanics not to be quite the right toolkit. So there's an idea floating around that thermodynamic resource theories are the toolkit that we're looking for these new systems. But how exactly that toolkit can be applied to these systems, which systems in particular, and whether really they can be applied is not entirely clear. I believe that the time is ripe to explore these questions. Here are just a few examples of some of the small systems that I mentioned earlier that over which people are exerting a lot of control. And since people have a lot of control over these systems, first they can test whether any of the effects of these so-called small-scale models are observable. And if so, then why aren't we using these models? Shouldn't we be applying them to these systems? If it is these systems that need to be described by this toolkit and that cannot be described by conventional statistical mechanics, can't we apply this toolkit in order to maybe push technologies farther? So I'll talk more about this DNA hairpin a bit later. I mentioned single electrons going through, or small numbers of electrons going through wires. So this work comes from Jukka Piccolo's group in Northern Europe. I'm very much a fan of that work. It's been used to test a lot of small-scale statistical mechanics, although not precisely thermodynamic resource theories. And here are just a couple of other platforms over which people are exerting a great deal of control at small scales. Suppose that by the end of this talk, I have convinced you, I have sold you on the idea that thermodynamic resource theories are the way of the future. You would like to model your favorite pet system with a thermodynamic resource theory. How do you do that? Suppose you want to specify or represent a system. You need to specify Hilbert space and a density operator rho defined on that space and a Hamiltonian H defined on that space. We assume that the agent is given access to a giant heat bath at some fixed temperature beta, some fixed temperature T or inverse temperature beta. Actually, we can generalize these theories more so that they model not only exchanges of heat, but also exchanges of, let's say, particles and maybe even quantities that don't commute with each other. Some recent work is in this direction. We said that every resource theory is associated with free states. We assume that the agent can draw for free from the bath any Gibbs state relative to that special inverse temperature beta. So the agent can dream up some Hamiltonian and create this state for free. It's just an approximation, a simplifying assumption. There's a star here because we usually assume that the Hamiltonian has a discrete bounded spectrum for mathematical simplicity. That isn't always very realistic, so I'll talk later about how sometimes I believe we should consider continuous spectra Hamiltonian if we want to edge these models closer to reality. And also, there are limitations even on discrete spectrum Hamiltonians that real experimentalists can create. There are a couple of reasons to believe that this assumption is sort of reasonable. Suppose that you are in an ordinary thermodynamic setting and you're given access to a giant temperature T heat bath. Suppose you have a system that's out of equilibrium. It's at a colder temperature. Suppose that you allow heat to flow between the two baths. Then you can, by running an engine cycle, extract work. And work is valuable. So if you have a temperature T heat bath, then non-equilibrium systems are valuable. They're resources. So it sort of makes sense that equilibrium states would be worthless, that you could create them for free. You would have all sorts of access to them in this simple model. Another reason to believe that this is reasonable is mathematical. So there are a couple of proofs that if any other state were free in this resource theory, the resource theory would be trivial in some sense. The free operations define the resource theories. The free operations in thermodynamic resource theories are often called thermal operations. They tend to thermalize states, surprisingly. They tend to bring states a little farther down toward those temperature T Gibbs states. Each free operation consists of 3 steps. The agent can draw from that bath any Gibbs state relative to that special inverse temperature beta and relative to any Hamiltonian. The agent can perform some unitary on the composite system that conserves its total energy. The agent can throw away some subsystem. But mathematically, each operation looks like this. The agent starts off with some state rho. The agent can tensor on some Gibbs state. The agent can transform the composite with some unitary. This is what I mean by energy conservation. It's sort of an implementation of the first law. When I write the Hamiltonian like this, I mean this sum. We might think, why just a sum? If we're doing ordinary statistical mechanics or condensed matter theory, we might expect to see some coupling term here. Well, that coupling is implemented by the unitary. It can sort of mix together the bath and the system of interest. Finally, we can discard any subsystem, which I label by A. Now I've introduced resource theories and thermodynamic resource theories, I'd like to introduce one-shot information theory, which is a mathematical toolkit applied to thermodynamic resource theories and all sorts of other settings. It's useful for describing small scales in some sense that I hope we will clarify during the course of this talk or in the Q&A afterward, and also strong correlations. Entanglement is a strong correlation, so it's one reason to have this in a Q+ talk. And also states that are not necessarily identical, are independent and identically distributed. Some tools in one-shot information theory were developed decades ago, but one-shot information theory was recently appropriated by the quantum information theory community. It's been quantized, and it's also been undergoing a great deal of growth during the past few years. It's being worked on across the world, and it's being applied to many different fields. A lot of information processing tasks, like into how small space can I compress some amount of data, how effectively can I transfer information across a channel. There are applications to security and also thermodynamics. What is one-shot information theory? Well, what is it not? It's not Shannon theory. From it we can recover Shannon theory. So, what is Shannon theory? Suppose that we are dealing with some random variable x or some quantum state rho. Now, suppose that you have many copies of this variable or state, and consider the limit as the number of copies approaches infinity. We call this the asymptotic limit. Suppose that you have all these copies, and you perform some joint transformation on them to perform some information processing task like compressing data. What is the maximal efficiency with which you can perform that task in this asymptotic limit? That is given by Shannon theory, and it tends to be a function of entropy. Here's an example that some of you might be familiar with of an information processing task whose efficiency is quantified by an entropy and which we will generalize. Suppose that I send you some random variable x, some letter from an alphabet of these possible values, x1, x2, and so on. X is distributed according to some probability distribution where p sub 1 is the probability that I send you letter x sub 1, and so on and so forth. I suppose that I send you many, many copies of this random variable. So n copies form this message m. In a limit as n approaches infinity, we approach the asymptotic limit. We'd like to know how efficiently I can compress this message into the smallest possible number of bits or units of information. The answer is I need I need Shannon entropy, number of bits, per copy of the random variable. This is how we define the Shannon entropy in terms of that probability distribution. We can tell similar stories about statistical mechanics and instead of information processing tasks, energy and statistical mechanical tasks. Often we have a system that's in one of many possible microstates labeled by I. The energy is the random variable we're interested in. The energy is distributed according to some probability distribution. One very popular probability distribution in statistical mechanics is the Gibbs distribution. This is how I'm going to define the Gibbs entropy. Granted, not quite everyone is very happy with this definition, but it's pretty widely used, so I'm going to take it for granted. But what about some thermodynamic task analogous to data compression? Suppose that you have a gas in a box, because many of us are physicists, and physicists love talking about systems in boxes. Suppose that this gas in the box can exchange heat with a giant temperature T heat bath through the walls of the box. Suppose that you compress the gas very slowly, quasi-statically, from this volume to that volume. Again, we would like to know the efficiency with which this process can be performed. That efficiency is given in terms of the work that's required to compress the gas. How much work do you need to perform? It's the difference between the free energies of these two states. And by free energy in this case, I mean the Helmholtz free energy. We can generalize to other free energies in other thermodynamic situations. That's given in terms of that entropy we were just talking about. And also, in general, a difference between equilibrium free energies can be expressed in terms of a relative entropy, although I haven't introduced that here. Note that the reverse process has the same maximal efficiency. So suppose that I start off with this compressed gas and I allow it to expand against the piston. It performs work to push the piston away. How much work is the most work I can perform? Again, delta F. So these two efficiencies of these inverse processes equal each other, the maximal efficiencies. That is not necessarily true in the small scale settings that we're going to talk about. But we were talking about data compression. Excuse me, just a moment. Since this is a Q plus talk, I should say something about the quantum version of the problem we discussed. So suppose that instead of sending you a random variable x, I sent you a quantum state rho. I sent you n copies of rho to form my message m, and we consider the limit as n approaches infinity, the asymptotic limit. Into how few qubits can I compress the message? Well, the number of qubits I need per copy of rho is the von Neumann entropy. The von Neumann entropy is this generalization of the Shannon entropy. That's the efficiency in the n approaches infinity limit. Now, I don't know about you, but I never have n approaches infinity copies of anything. So I'm not sure how very useful this optimal rate is. In fact, sometimes we only have one shot. I'm not sure how familiar or how many fans we have in the audience of the rapper Eminem, but in this case, I think that some of his lyrics encoded a very deep message. So as he says, sometimes you don't get n approaches infinity copies of a quantum state. Sometimes you only get one shot. So you should not miss your chance to blow, because this opportunity comes once in a lifetime, yo. So what lesson should we draw from our friend Eminem the rapper? Sometimes it's useful to describe the optimal efficiency with which we can perform information processing tasks on not just n approaches infinity copies of a state or a variable, but arbitrary numbers, including small numbers or small scales, and including just one shot. When we talked about Shannon theory, we said that efficiencies were quantified in terms of the Shannon entropy or the von Neumann entropy. Here also, entropies are useful for quantifying maximal efficiencies. But in one-shot information theory, we use a whole family of entropies. One subfamily is the family of Renyi entropies. It's a relatively simple example, so I'm going to focus on those in this talk. The Renyi entropies are characterized by an order alpha. Alpha is some number usually considered to be positive. Here's the definition of the order alpha Renyi entropy. I still think it looks a little bit bizarre, but at least it has a log in it. That's sort of comforting. Entropies tend to have logs in them. And we can become even more familiar with it by considering a simple case. I'm going to focus on 3 Renyi entropies that are applied particularly often in thermodynamic resource theories. One is the order 1 Renyi entropy. In the limit as alpha approaches 1, this denominator causes the fraction to explode. But if we take the limit properly, we find that this limit yields the Shannon entropy if the argument is classical, or the von Neumann entropy if the argument is quantum. So in a particular limit, this funny-looking definition gives us back the entropy we know and love. There are a couple of other entropies that will be useful for us. The order 0 infinity is sometimes called the max entropy. Now, granted, nowadays it's a little more hip to call the order 1/2 Renyi entropy the max entropy, but they're close enough. What is the expression for this entropy? Well, suppose that rho is a quantum state. It has support of some dimension, so this is the dimension of the support, or the number of non-zero eigenvalues of the state. The log of that quantity is the max entropy. If we consider a probability distribution instead of a quantum state, then this is just the number of non-zero values of the distribution. Max entropy has applications in a number of different tasks. One is we can return to that data compression example. Suppose that we are interested in compressing some finite number of copies of a quantum state or random variable. Then the maximal efficiency with which we can perform this task is given by the max entropy. There's also an application to thermodynamic resource theories that we'll discuss in more detail. Suppose that we start off with some non-equilibrium state, which is sort of analogous to this squeezed gas. Suppose that we extract from that state all the work possible. That's analogous to allowing the gas to expand against the piston. What is the maximum amount of work that we can extract from this process? That's quantified more or less by the max entropy. Final entropy that we'll need to discuss is the min entropy, the order infinity Renyi entropy. Here, Pmax is the greatest eigenvalue of the quantum state rho, or the greatest value in the probability distribution P. One application it has is to randomness extraction. So suppose that I give you a few copies of some probability distribution. This distribution isn't pure and it isn't maximally mixed, but you would like to extract from it as much randomness as possible, as large a uniformly random state as possible. What is the maximal efficiency with which you can do that? Well, first of all, why would you care? You might want to extract randomness because people need random number generators, because randomness is useful in cryptographic applications to security. That's one reason to think that randomness might be a valuable resource. So we might want to calculate the efficiency with which we can perform that extraction task. That efficiency is given by the min entropy. In thermodynamic resource theories, the min entropy helps quantify the work required to create some non-equilibrium state from just free operations and the specified amount of work. That's analogous to starting out with this uncompressed gas and expending some amount of work to compress it. Let's compare our discussions of Shannon theory and ordinary statistical mechanics to thermodynamic resource theories and one-shot information theory. In ordinary statistical mechanics, the work cost of creating a state also equals the work extractable from the state. That equals a free energy, which is proportional to a change in, that's equal to a change in free energies, which is proportional to a difference between entropies. Or alternatively, you could express this as a relative entropy. Suppose you were interested in some initial states, maybe of the gas, and some final state of the gas. You wanted to know if the gas could transform from this initial state to the final state. We would advise you to evaluate the free energy of the initial state and the free energy of the possible final state, see whether the free energy increases, decreases, or remains constant. The second law would tell you whether the transformation can occur. In contrast, in thermodynamic resource theories, this work cost is related to the order infinity Renyi entropy, and the work yield is related to the max entropy. So two different entropies quantify two tasks that are the inverses of each other. That's different. Also, we can think about transformation laws, and here's how we would phrase those in terms of thermodynamic resource theories. Suppose you start off with a state rho, h. You're interested in seeing whether it can transform under thermal operations to a state sigma, h prime. In this case, you would have to calculate a whole family of free energies of the initial state and free energies of the final state. Free energies are given in terms of some of these entropies. You would have to check whether a whole lot of inequalities are satisfied. These are sometimes referred to as second laws. So these are some of the differences between ordinary stat mech and information theory and one-shot stat mech and thermodynamic resource theories and information theory. Though from this framework, in the appropriate limit, you can recover this framework. So now that we've talked about one-shot effects, what are some of the ones that we might want to realize physically? Or what does it mean to realize them physically? First, we'd like to see signatures of one-shot entropies, such as the Renyi entropies, that differ a great deal from each other, and also from the Shannon entropy or von Neumann entropy. In particular, we would like for some of those one-shot entropies to be non-zero, so that we could observe their signatures. Here's an example of what I mean. Consider this probability distribution. It has a large value of 1/2, and all of the other values are quite small. So suppose that you plotted out this distribution as a histogram. One of the values would be 1/2, it would be rather tall, and all of the other values would be very short. So this distribution would look like an L, hence the name. We can calculate the entropies of this distribution. The min entropy has this definition, recall. This is the greatest value of the distribution, which is 1/2. So if we substitute in 1/2 here, we find that the min entropy is 1. In contrast, consider the max entropy. It's the log of the number of non-zero elements. All of these elements are non-zero, and there are d elements. So the max entropy is log d, which is a great deal larger than the min entropy. So here is a state that has a discrepancy between two of these one-shot entropies. Now this is a classical probability distribution, but you can always consider purifying it by Stein-Spring dilation. That purification would be the entangled state of the many-body system. So there can be connection to quantum information theory, and in particular the relationship between the classical and quantum components of thermodynamic resource theories offer various opportunities for realizing different parts of this model physically. So again, these are what we might want to look for in physical reality. So what are some of the applications in thermodynamic resource theories? We already talked about how the work costs of creating a state can differ from the work extractable from a state. I mentioned some second laws. Here I'll provide a little bit more detail. Suppose that you were interested in just quasi-classical states in which rho commutes with h, so all the operators commute, there are no quantum effects. Still, if we're talking about this small scale limit, you would have to check that a whole bunch of inequalities are satisfied if you want to see whether one state can transform into another state. There's another family of second laws if rho and h have coherences relative to each other. So rho is not diagonal in the energy eigenbasis. There are so-called second laws for coherence. There's even an opportunity to do more theoretical work on that topic. And lately we've quantized this even more and considered laws associated with a whole bunch of quantities that don't commute with each other. So those are some of the applications. Let me walk you through one of the applications. And we saw the front of this paper earlier. It's one of those 2013 foundational papers. So I just want to show how this one-shot information theory toolkit is applied within thermodynamic resource theories. Suppose that you are the agent in some thermodynamic resource theory, and you would like to create some state rho, h. For simplicity, we'll suppose it's quasi-classical. You need to perform free operations, and you also need some amount of work. Suppose that you have a friend out in the hall who's very rich, has a whole lot of work, and says, I'll give you a battery to create the state you want if you tell me how far to fill up the battery. So you'd like to calculate that amount of work. Actually, I'll generalize the problem a little bit. I'll say, you wouldn't mind creating some state that's very close to rho, comma h. Suppose that d is some distance measure like the trace distance. The distance between the actual state and the target state should be within some tolerance. You would like to calculate the least amount of work required to create any of these approximating states. I'm going to denote that work by this quantity. I haven't actually defined work in thermodynamic resource theories. I'm not sure if anyone's noticed, but it is something that needs defining. This is a very simple model that's often used in thermodynamic resource theories. It's called a work bit, or sometimes called a WIT for short. I'm sure that the coming up with that shortened phrase was very witty. It's a two-level system that has an energy 0 and an energy W. We assume, for simplicity, that this battery always occupies some energy eigenstate, where E can be the ground state energy or the excited state energy. And this is a Hamiltonian. I'm going to say this is my battery. If I'm going to create a state, then I start off with a battery filled, and I end up with a battery empty. Just a moment, I need to take a drink. This was our guiding question. Let me phrase it a little bit more mathematically. What is the least amount of work such that you can start off with a filled battery, you can tensor on some free states, you can transform the whole by some unitary that conserves the total energy, and you can discard some subsystem such that the resulting state is very close to the state that you wanted. What's the least amount of work required to perform that operation? I'll give you the answer. Don't worry, I won't take you all the way through the derivation. Actually, I'll give you an approximation to the answer. It's not quite correct, but I don't want to have to introduce even more entropies into this talk. So roughly, we need this amount of work. This is some energy dimensionful factor. This is the log of the dimension of the space on which the state is defined. And this is some entropy. It's built from the min entropy. There's this epsilon here, so I didn't actually define this quantity, but it's just some generalization of the min entropy called the smooth min entropy. That's the work cost of creating a state, approximately. We can ask about the reverse process. I warned you we would. Suppose that you started off with some state rho comma h, and you wanted to extract from it as much work as possible with some approximation in there. What is the most work you can extract? Again, we have this energy dimensionful factor, we have the log of the dimension of the space, and we subtract off this smooth max entropy. Here's the min entropy, here's the max entropy. These two thermodynamic tasks that are sort of inverses of each other have optimal efficiencies given by different entropies. This is a signature of one-shot information theory. So if you take the appropriate limit in which there are many, many copies, take the limit as n approaches infinity, then the work cost, so the optimal efficiencies of these two processes approach each other, and they approach the difference, well, some difference between free energies. The takeaway is that one-shot information theory gives us new results about so-called small scales, but from it we can recover statements about large scales that sort of make sense according to what we know about ordinary stat mech. I said, now is the time to explore some of these effects and try to observe them. Remember, some of the motivations for this work are experiments, great control over systems, small-scale systems, and the possibility of nanoscale technology. I think it's worth testing if the scales that are supposedly right for these theories are actually right. I haven't actually seen even a back-of-the-envelope calculation that indicates what precisely is the right scale for these theories. I think that calculating that scale would be useful. It would be useful to find out, are the technologies that we have now the right scales for these theories, and are these the scales that aren't suited by ordinary stat mech and Shannon theory? Or do we have to wait 10 years till technologies will bump up against these fundamental limitations, as people say they might be about to, or maybe hope might be about to? Or will we never reach these scales, the scales at which these fundamental limitations become apparent? If not, well, sure, it's definitely worthwhile to explore the fundamental limitations on what is ultimately physically possible, but we might also want to redirect some of our energies. On the other hand, if we find that people are bumping up against these fundamental limitations that require us, supposedly, to use thermodynamic resource theories, then let's apply the thermodynamic resource theories. Let's apply them to experiments and hopefully use them to explore new technologies. I'm going to suggest some steps for bridging the gap a little bit between theory and physical realization. So I come at this from a theorist's perspective. I don't yet have as much familiarity with the experiments as I would like to have. However, I know some of the questions that need asking. So I'm going to ask some questions of experimentalists and some of theorists. For details, you can see this paper. Resource theories were constructed in part to reflect real-life limitations. For instance, it has been difficult in labs to create controlled entanglement, and that's one motivation for entanglement theory. Similarly, we are limited by energy preservation in the first law. Thermodynamics itself was a study of what people could do with engines and what they could not do. So to some extent, these theories are supposed to reflect and shed light on what we can and can't do. I've talked with a few experimentalists who might have different priorities, even thermodynamic experimentalists. For instance, some people will say, you assume that the agent can perform any energy-conserving unitary. That's an awful lot of control. Some of these many-body unitaries are actually difficult to perform in a lab. I'll talk about baths a little bit later. One point on which experimentalists and thermodynamic resource theory agents might agree is coherent operations. So according to the second laws of coherence that I mentioned earlier, the amount of coherence in a system, according to some measure, only decreases monotonically under thermal operations. It's difficult to create coherence relative to the energy eigenbasis. Similarly, in quantum computers, one of the greatest challenges is fighting decoherence. That's promising collision between priorities. Similarly, some experimentalists don't really care about how much work they spend, whereas work is valuable in thermodynamic resource theories. But I even talked to one thermodynamic experimentalist who said, what do you mean work? What would you mind explaining? Are you sure I'm spending work? What are you talking about? And I said, well, suppose that you turn on some, say, electric field. And technically what you're doing is bringing electric charges from very far away to very close to your system of interest. Each time you bring a charge, you have to do work against the electric field already built up by the charges present. So technically you're doing work. And he says, oh, okay, yeah, I do see what you mean. But I don't care. I don't keep track of the amount of work that I perform. That's not a resource to me. Some experimentalists are much prouder of being able to impose a field on some well-defined space for some well-defined time. So we could incorporate into thermodynamic resource theories some of the priorities of real thermodynamic experimentalists. On the other hand, we might say, well, maybe they have difficulty with some supposedly free operations now, but they're very clever. They'll figure it out soon. We don't need to adjust the theory. But I suspect that a compromise might be useful. Finally, when an experimentalist performs a unitary, the experimentalist cannot perform it exactly precisely because of lack of control over the system. This is a known problem in quantum error correction. So we might think about, within thermodynamic resource theories, coarsening the set of free operations, supposing that the agent doesn't have so much control over the system. Some strides were made in this direction recently. I know Chris Perry signed up to be in this talk. I'm not sure if he's in the audience at the moment. If so, let me give a shout out to Chris and his group. This is, I think, a useful step on the road. It would be great to bring that even farther from theory to what experimentalists can really perform. Some promising platforms for physically realizing thermodynamic resource theories consist of condensed matter or quantum optics. The natural language for these systems is that of quantum field theory. Quantum field theory has not really been incorporated into thermodynamic resource theories. A few initial steps have been made, but number one, this could be a fun theory challenge. And number two, it could be quite useful for the modeling of real physical systems with thermodynamic resource theories. I mentioned baths. There are a couple of problems here. One result in thermodynamic resource theories that is used over and over again is a transformation becomes exact in some sense, and a limit as the bath's size approaches infinity. Now, I don't know about you, but I never have an infinitely large bath around. Granted, this problem is not limited to thermodynamic resource theories. In ordinary statistical mechanics, we run up against the finite size problem. Therefore, it might be useful to take some of the techniques from ordinary statistical mechanics and apply them to thermodynamic resource theories to introduce corrections into results. Also, an experimentalist cannot necessarily design the required bath. I heard from a quantum dot experimentalist, no, I can't just build any Hamiltonian I want. I have the Hamiltonian of the system that I have. So incorporating that into thermodynamic resource theories might help bridge the gap. I'm not going to say much about embezzlement. I will say, when I finish this talk, if we are asked for questions and there is an awkward silence, then feel free to ask about this question to break the awkward silence. The embezzlement problem is a problem talked about a fair amount by thermodynamic resource theorists. So it's considered to be an important problem. It's a phenomenon that is predicted by thermodynamic resource theories. On the face of it, this phenomenon seems impossible, but if you look closer, it's actually consistent with the laws of physics, of course. But because it's so surprising and it involves a fair amount of control, I think it would actually be fairly interesting if someone could realize this experimentally. So there are two ways to go. One is eliminate this from the theory, and the other option is embrace it and try to realize it, and try to realize a difficult and perhaps surprising looking experimental result. There is another toolkit for small-scale thermodynamics called fluctuation relations. Fluctuation relations are theorems developed in statistical mechanics, and they describe systems that overlap a great deal with the systems supposedly described by one-shot information theory and statistical mechanics. Both frameworks describe systems that are small in some sense, both describe non-equilibrium statistical mechanics, and both involve some what people think of as a new derivation of the second law. Fluctuation theorems have the advantage of having been experimentally tested quite a bit. These are some of the platforms that have been used to test those results. This is DNA hairpin, one of the first platforms used to test fluctuation theorems. So this is a string of DNA. Someone fixes this leg and pulls this other leg. You can calculate the amount of work that you have to do to pull the pin apart. Then you can, so that's like calculating the amount of work required to create a state or required to compress a gas. You can let the leg fall back. Then you can calculate the amount of work extracted. So since fluctuation theorems have been realized experimentally, and they have overlap with thermodynamic resource theories, we might use fluctuation theorems as a bridge from thermodynamic resource theories to physical reality. A few steps have been made in this direction, and it's a lot of work. Well, a fair amount of work is happening on the subject now. I really hope that it will continue. I personally am not certain how to make the bridge, but I think it could be promising. One possible platform that looks somewhat promising for realizing thermodynamic resource theories consists of quantum optics, for example. Imagine this is some electromagnetic mode in a cavity. So this is a mirror, maybe this is a two-level system interacting with the electromagnetic mode. Suppose that this mirror is leaky. Some of the field interacts with the electromagnetic continuum in the surrounding room. Now notice I said continuum. A lot of real physical systems have continuous spectra. And recall that I said that when using thermodynamic resource theories, we tend to assume that the energy spectra are discrete and finite discrete and bounded for mathematical simplicity. Well, now might be the time to step from these mathematically simplifying assumptions toward more realistic assumptions. Even some, well, quite a few classical systems have continuous spectra, for instance, the simple harmonic oscillator. So it would be useful to rigorously incorporate continuous spectra into TRTs. I have 1 minute left. Almost finished with my slides, so don't worry. Now, a lot of statements derived from TRTs are about optima. We talked about the maximum amount of work extractable and the minimum amount of work required to create a state. Now, optima are not experimentally realizable, so would be difficult to test these. But again, that is a problem not limited to thermodynamic resource theories. The Carnot efficiency, a very old thermodynamic result, is about the most work extractable from an engine, or the greatest efficiency of an engine. So we can pull over the techniques from these other problems. For instance, this is a plot from a paper by Yuka Piccolo's group. They were testing Landau erasure, which is a fundamental limitation on how much heat is dissipated if you erase 1 unit of work. So that ultimate limit is reached in the quasi-static limit as the process is performed very slowly. So they performed a process at some high speed, at a lower speed, at a lower speed, and so on. As they dropped the speed, their efficiency dropped toward the optimal limit. Maybe that seems like a kind of obvious strategy, but people haven't been thinking about this in the context, well, not enough, I think, in the context of thermodynamic resource theories. And this is this is a way of thinking that could make TRTs more practical and realizable. And a lot of TRT theorems are no-go theorems. It's also kind of difficult to prove a negative with experiments. There might be a few ways around that no proving a negative in some cases, but they would be a little tricky to find. So first we need to figure out which of our results, which of these marvelous theorems that have piled up over the past few years can be physically realized. I mentioned that the simple battery model is not necessarily the most realizable in an experiment because you can't necessarily tune this gap exactly as you would like. There are a few opportunities with measurements and distances, that epsilon that I mentioned before. In summary, we talked about thermodynamic resource theories, a model for statistical mechanical exchanges of heat and particles and so on, including at small scales, for some meaning of small scales. We talked about one-shot information theory, a mathematical toolkit that is applied to thermodynamic resource theories and other contexts. It would be great to realize these experimentally. We would like to observe signatures of one-shot entropies that differ from each other, that differ from the ordinary Shannon and von Neumann entropy. And, excuse me, I was just noticing that text came up on the screen. And in particular, that are non-trivial, are non-zero. I argue that now is the time to try to realize thermodynamic resource theories and one-shot statistical mechanics physically, because now we have these technologies that have been motivating the theories. It'd be great to find out if we could really apply these models to these theories, apply these models to these experiments and maybe help guide them. I suggested some steps, some questions to ask about shifting these models closer to physical reality. So thanks very much for participating.
Excellent. Thank you very much, Nicole, for this very nice talk. So we're now starting to model the questions. So we have about 15 viewers online. So if those of you who are watching the live stream, if you could type your question on the event page, and we will bring it into the Hangout. And then for those of you who are here with your webcam inside the Hangout, please type in the chat to announce that you would like to ask a question, and then I will direct Nicole to you. So maybe I will start with the first question, which is rather simple and technical. But so you mentioned that the free states are arbitrary Gibbs state of the bath in arbitrary Hamiltonians HB, right? So is there no constraint on HB? Because what's the role of beta then? I mean, I can always put the beta in HB, can't I? Or is there some norm constraint on HB?
The idea is that beta is fixed. So the agent has access to some giant reservoir at a fixed temperature, and then the agent can choose any Hamiltonian desired and make a Gibbs state relative to that inverse temperature.
Right, but then, I mean, if I can choose arbitrary Hamiltonians on the bath, I can just absorb beta into that. I can just make the Hamiltonian stronger to get a different effective energy, can't I? I mean, or in other words, doesn't that mean that you can get arbitrary bath states as long as they have maximum rank? Because you can basically just take the logarithm of the bath state and you will always find some Hamiltonian that has that as a Gibbs state. Maybe I'm overlooking something.
Well, that would give a different temperature. So physically, the idea is that the atmosphere around you has just one fixed temperature, and if you were thinking of, sorry, it seems that there's some feedback. It's strange.
Yeah, just a second to fix that. Kishore, can you mute your microphone? Oh, it's already done. Okay, that's fine. Yeah.
Okay, so the temperature can't just be absorbed into the Hamiltonian. It is a constraint. So if you tried to make a different temperature, then that would automatically be a resource state. And there are a couple of places in which this is derived. One is a paper I wrote with Joe Renes, in which we showed that the ambient temperature has to be respected. And another place is this paper, Second Laws, by Fernando Brandão et al. They use an argument from complete passivity to show, okay, there the temperature plays sort of a funny role, but they show that the Gibbs state has to be the form of the free state. If any other state were free, then the resource theory would be trivial in the sense that from a non-equilibrium from non-equilibrium states, you could create other non-equilibrium states. So there would be sort of no order to the theory, and from just free operations, you could get anything you wanted. And that's quite unphysical.
Okay, thank you very much. Well, as you can see, Carlo has requested, and I agree with that request, if you could talk a bit about the thermal embezzlement stuff that you mentioned. Okay. That sounds really interesting.
There's the hook that I left, yes. Okay, it's a little bit easier if I have access to a board that I can write on, but let's try it without the board. So here's the idea of catalysis. Embezzlement is related to catalysis, and catalysis is a phenomenon that is known to occur in a number of resource theories in general, including the entanglement theory. What is catalysis? I suppose that, well, for the moment, I'm not going to think about the Hamiltonians, just for simplicity. Suppose that we're interested in an initial state rho and initial state sigma, or excuse me, a final state sigma. Suppose that we would like to transform rho into sigma by free operations. Suppose that that's impossible according to the transformation laws of our model. There is a possibility that you could use some other state, a catalyst, let's call it Xi, such that rho tensored with Xi transforms into sigma tensored with Xi. So Xi, this catalyst, facilitates the transformation but is not changed during the transformation. In ordinary thermodynamics, we could think of it as an engine. So suppose that you have two baths and you have an engine in between. Then you can use the engine to extract work and to change this two-bath system into work. But the engine itself is not transformed. So that's the idea of a catalyst. I apologize, I'm a little bit distracted by the text running at the bottom of the screen. So that's responsible for the pauses. So that's perfect catalysis, but we might think perfect catalysis is not possible in physical reality. How come? Because we would always expect an engine to degrade a little bit during transformation. It's never going to be untouched. So suppose that we allow in our theory for the engine for the Xi to turn into some Xi tilde that is very close to Xi. Then we would have to explore the implications of allowing this transformation into the theory. It turns out if you have a large enough catalyst, then you can extract as much work as you want. even if you degrade the catalyst only a very tiny bit. That's seen as a problem because it seems like you're extracting a ton of work, something very valuable, by degrading something only a tiny bit. And it seems like we're getting a lot from almost nothing. So there, it's physically unexpected. But it is physically possible because we are degrading the catalyst a little bit. And if the catalyst is very, very large, then it's like we have access to a large resource, and we just barely notice when it changes, but it really does degrade. So you can change around some definitions and maybe distance measures to introduce some constraints so that the picture seems more physically expected. But in this case, all of those one-shot entropies become irrelevant. And all you need to do to check whether a transformation happens is check those von Neumann type entropies, the ordinary Shannon entropy type entropies. That's kind of dissatisfying because thermodynamic resource theories are intended to describe these small scales characterized by one-shot entropies. So that solution doesn't seem so satisfactory. But people have been exploring other distance measures, such as the work distance, which is sort of the amount of work that you would have to invest in order to restore the catalyst to its original state. And so people are sometimes demanding that the catalyst end up to within a work distance measure, like W tilde, of its original state. That's one possibility. Although that's also not entirely satisfactory because the work distance doesn't have nice properties of entropies, relative entropies in particular, that we're used to. Excuse me, it doesn't have nice properties of other distance measures like the trace distance. So which distance measure is appropriate in a thermodynamic context is not entirely clear. There are plenty of people who really just want to eliminate the embezzlement problem, as I call it, from resource theories. There's a talk. The one-shot information theory community has an annual conference called Beyond IID. This past summer, it happened in Banff. During the open problem session, Jonathan Oppenheim gave a presentation about how the embezzlement problem needs to be eliminated from TRTs. That's one way to look at the problem. The other way to look at the problem is, yeah, embezzlement is unexpected, but great. If you can realize that physically, then that's kind of surprising, and it would mean that the experimentalist has exerted a lot of control over the system. So it would be a fun challenge for experimentalists. So I'd really like to see someone realize it personally.
Okay, thank you. As you can see, there's a written question here by Kishore, who wants to know more about the motivation behind different entropys for work costs and cost yield in the theory, especially because the entropies are supposed to be the same in StatMech. So if you can elaborate on the physical reasoning behind. And if I can just remind others, if you have any other questions, please type in the chat, and then I'll direct you to them.
The question seems to be about how come different thermodynamic tasks in thermodynamic resource theories are have efficiencies quantified by different entropies. So that comes from the idea of this one-shot limit. It's because we're considering the transformation of just one copy of a state row. In ordinary statistical mechanics, we're thinking about averages. So this is something that I talk about quite a bit in, I think, the technical introduction of my paper, and I try to lay it out fairly cleanly. So if the next couple of minutes don't clarify things, that might help clarify. So in statistical mechanics, ordinary statistical mechanics, we think of averages in a number of ways. Averages over trials, for example, and averages over many, many particles. So we can use statistics at all in statistical mechanics because there are so many particles that we can assume that particles just act like the average. That only works in this large scale limit. If you're thinking about just one copy of a state row, then you cannot assume that it acts like the average. So you need to use arguments about sort of the worst case or the best case in order to calculate the guaranteed work. But if you take the right limit of the one-shot theory, then you can recover the results results like those in ordinary StatMech. I actually have a few slides about this at the end of the presentation, I don't know if you would like to see those at the moment. I just put them in case someone asked a question like this, but I don't know if I've taken too long with a question already. Let me know.
Kishore?
Yes, please. Okay. Sure, let me go back into screen share. Okay. I'm glad you asked this question. So let's go back to the end of the part of the talk about work extraction and state creation. We were talking about one copy of a state, rho comma h. Now suppose that we want to create many, many copies. So I'll denote many, many copies like this. So here are many copies of a density operator, and here are many identical Hamiltonians summed together. Let's take the limit as n approaches infinity, so we get back into that asymptotic limit described by ordinary stat mech and information theory. This is our guiding question. It's similar to the question that we asked about data compression, which was what is the least amount of information, the smallest number of bits into which we could compress per copy of the random variable. So this is a similar sort of question, which signals to us that we should get a similar sort of answer, namely one that involves an ordinary entropy. If we take this limit, so we start off with, let's say, the work cost of creating this very large state, epsilon approximately. I said we're interested in the average per copy, and we take this asymptotic limit. The limit of this work cost approaches the limit of the work extractable. Both of those we can calculate by substituting into formulas like the ones that I presented earlier. We use a tool called the asymptotic equipartition theorem, which also has far too many syllables in it. The result is each of these quantities equals this energy dimensionful factor times a relative entropy. Relative entropy between the state of interest and the equilibrium state over the same Hamiltonian. And we know the definition of the relative entropy, so we can substitute in gamma equals this equilibrium state. And we do some algebra, and then we do some more algebra, and we end up with this expression, which looks kind of funny, but it's actually not so bad to parse. This here is an average energy, this is a temperature, and this is a thermodynamic sort of an entropy. This looks a lot like the definition of the Helmholtz free energy. So some people call it the Helmholtz free energy of this non-equilibrium state rho. And this, in fact, is the Helmholtz free energy of the equilibrium state. So in this limit, the average work costs and the average work yields come to approach each other and come to approach a difference in free energies, which is what we'd expect. So in this appropriate limit, the one-shot results come to approach the ordinary stat mech results. But we do need to be very careful about what we mean by one shot and one copy.
Okay, excellent. I think it's time to conclude. Let's thank Nicole again for this excellent talk. You know, clapping is always something that is a bit difficult inside the Hangout, so I'm going to clap representative of the whole audience. As usual, then we stick around a little bit longer. That's kind of the conference coffee break, so to say. So you're welcome to stick around if you have some feedback about Q+ or about future speakers that you'd like to see or anything else really, then stick around. But I'm going to stop the broadcast right now.